Hello and welcome back. My name is Jerry, and last I remember we were studying projectile motion. Now, up to where we had done last time, we had simplified the problem by assigning a vector to the velocity of the ball, and we had simplified the velocity further by dividing this arrow that was doing two things, rotating and changing in length, into two simpler arrows. One, the vertical component of the arrow of the velocity that's only growing and shrinking, and two, the horizontal component of the velocity that doesn't seem to be doing anything. Now let's go ahead and analyze these two components separately and see what we can learn about the flight path of the ball from both of them by themselves. The vertical component of the velocity. Now, the vertical component of the velocity, if we were to view it from this side, smack in the front, and remove the perception of depth, it would look like a ball being chucked straight up, slowing down, and then speeding up again as it's coming back down. So let's treat it this way. Let's treat it as a one-dimensional problem and see what we can learn from that. So let's go to the boogie board. We had already established that the muzzle speed, the speed at the muzzle vertical velocity. Hold on, pause it at the right moment. Okay, that's not the right moment, but yeah, right there, just as it leaves the gun, we had realized we had managed to figure out that the vertical velocity, a part of the velocity that was vertical as the shot was fired was v sine theta. So the initial vertical velocity as it leaves the gun is v sine theta. And now we want to write an equation for the displacement of this as it travels through the air. So now as it's traveling vertically, go back to this view. As it's traveling vertically, the only thing that's influencing its flight path is gravity. Gravity is the only force that's acting on it in its entire vertical flight path, and therefore acceleration will only be because of gravity. But we have defined our positive directions as positive x, and this is positive y as our default positive directions, but gravity is pointing downwards, so therefore this we can't write. We'll have to write gravity as acceleration as minus gravity, which is equal to minus 9.8 meters per second square. I think in feet it's 32 feet per second square, so minus 32 feet per second square. Anyway, that's not important, we'll be working in the metric units. So anyway, so our displacement equation, s is equal to ut plus half at square, becomes s is equal to v cos theta, no sorry, this is v sin theta, forgive me, v sin theta into time minus half g times square. This is the general equation for vertical displacement. So we can plug in any amount of time into this equation. All we have to do is plug in a time in this equation and it will tell us how high the ball is. So this is displacement in height, which is equal to v sin theta into t minus half g t square. This is a general equation for how high you will be at any point in time during the flight. Now let's analyze it further. We should also be able to tell how much time it takes to reach its highest point. Two interesting things about the highest point. When it starts off, it's got v sin theta as its initial vertical component, and when it reaches its peak, its final speed at the peak is 0. So your initial speed, I'm going back to the boogie board, initial speed is equal to v sin theta, upward speed in any case, and your final speed is equal to 0. How much time did you take to reach this? Let's call this the time it takes to reach the maximum height. So v is equal to u plus at, and therefore 0 is equal to v sin theta minus g, because remember acceleration is equal to minus g into t, and therefore adding gt on both sides, gt is equal to v sine theta, and therefore time it takes to reach its maximum height is equal to v sine theta by g. Brilliant. Now the next part of the problem, we want to find out how much time it takes to cover the entire flight path. Now, just based on symmetry, an argument based on symmetry will tell us that if this is the amount of time it takes to reach its maximum height, then this, the amount of time it will take to complete its entire flight, will be double that. So just based on symmetry, we can say that the total time of flight is equal to twice the time it takes to reach its maximum height, and therefore time of flight is equal to 2v sine theta by g. We arrived at that solely based on symmetry. But if you are not satisfied by the argument of symmetry, then you can arrive at the same answer in a different fashion. Observe from this angle. The speed at which it leaves the gun, the speed at which it leaves the gun is v sine theta. It's got v sine theta as it leaves the muzzle, but by the time it reaches there, by conservation of energy, it's got the same kinetic energy it had when it left the gun. So if it had an upward kinetic energy of v sine theta, it will have a velocity of equal magnitude in the downward direction when it comes here. So if this was v sine theta, your initial was v sine theta, your final will be minus v sine theta, and therefore based on the argument of conservation of energy, u is equal to v sine theta implies v will be equal to minus v sine theta by the time it reaches the other end, and therefore acceleration is equal to minus g. So and time is equal to the total time of flight. Therefore we have v is equal to u plus at minus v sine theta is equal to v sine theta minus gt. Adding gt on both sides and adding v sine theta on both sides, we get gt is equal to 2v sine theta, and therefore the total time of flight is equal to 2v sine theta divided by g. There we arrived at the same equation for the time of flight in two separate arguments, and therefore both arguments are separately and together consistent. Which means that now we have the knowledge of two things: the general equation of three things: the general equation of displacement, half the time of flight or the time it takes to reach its maximum height, and total time of flight. What else can we figure out from these equations? We can also figure out from these equations, wait, bring back the perception of depth, the maximum height that it reaches. Yeah, see, at this maximum height we already have a general equation for height that it reaches. Now in the general equation for the height that it reaches is equal to v sine theta into t minus half gt squared. The time it takes to reach this middle position is the time it takes to reach its maximum height, or half the time of flight. So if we plug this half time of flight into this equation, we should be able to get the maximum height, because arguably the maximum height is at the center of the flight path, and therefore if we plug in this time to reach the maximum height into this equation, we get maximum height is equal to v sine theta into the time it takes to reach its maximum height minus half g time it takes to reach the maximum height squared, and we found the time taken to reach the maximum height is equal to v sine theta divided by g, and therefore maximum height h is equal to v square sine square theta divided by g minus half v square sine square theta minus by g squared. Just plugged in the values, and therefore 1g cuts with 1g here, and therefore maximum height is equal to v square sine square theta by g minus half v square sine square theta by g, and therefore maximum height is equal to half of v square sine square theta by g. So now we have four important equations within our grasp. An equation that tells us the vertical displacement. So far I've been using SH to represent displacement in height, but I realized that will cause confusions later, because I've got to use SH to mean horizontal displacement. So I'm shifting from this nomenclature to SV to mean vertical displacement, and later on in the next video I'll use SH to mean horizontal displacement. I'm sorry for the confusion in nomenclature. Anyway, moving on. So let's write down the four equations that we managed to figure out so far. Vertical displacement is equal to v sine theta into time minus half g time squared. This is 1. Then we have the time it takes to reach its maximum height, which is equal to v sine theta by g. This is the second one. The time it takes to complete its total flight path is 2v sine theta by g, total time of flight, and the maximum height it reaches is half v square sine square theta by g. Brilliant. All this we've been able to tell about the vertical displacement, vertical flight path of the ball, simply by this vertical component of the velocity, and we've milked all that we can about the flight path of the ball by studying only the vertical component of the velocity. And in the next video I will show you how we can learn all that we can about the horizontal displacement of the ball using the horizontal component. See you then.